Hello everyone, thanks for the quick intro. So today I'm going to be talking about self-auditable key transparency and a couple of recent works that we have on it. So let's first see what key transparency is and what is the motivation behind it. So imagine John and Egret are texting each other on an end-to-end encrypted messaging app such as WhatsApp. As long as they have each other public key, the service provider only transmits ciphertexts and cannot decrypt them. But the very fundamental question here would be, where do they get each other public keys from? Assuming initially they have each other mobile phone number, how do they map the mobile phone number to the public key? And we just cannot assume that the service provider will distribute these public keys because the service provider might be faulty and give John the public key of the Night King instead of Egret. Here the Night King will be impersonating Egret without John ever realizing it, which may end up in some awkward situation for three of them. So one traditional solution to this problem of public key distribution that currently iMessage, WhatsApp, and Signal all supported is the assumption that the users can obtain or verify each other public keys out of band, for example, by verbally comparing a string of words or scanning a QR code on their phone. But these are all very manual solutions. For example, it may require meeting your contacts in person, or every time someone public key changes, they must rerun this manual verification with all their contacts, which makes the user experience less ideal. At a high level, key transparency proposes an automated solution for this. So, to elaborate this simple model of key transparency, assume we got three parties here. We got John, we got Egret, and we got the service provider. Also assume there exists a bulletin board that all the parties can observe it, and the service provider can post messages on it. So what happens is that the service provider periodically posts signed commitments to the directory on the bulletin board. And whenever John queries public key of Egret, it receives the public key along with a proof. What is the use of this proof? Well, via the proof, he can verify that the public key is indeed consistent with the commitment on the bulletin board. And the really cool thing here is that it allows the public key owner here, which is Egret, to actually monitor what public key is being advertised for her username. So similarly, she would just query her own public key, she's going to receive it along with a proof, and via the proof she can actually verify it's indeed consistent with the commitment on the bulletin board. And this whole solution is automated and it requires no manual effort neither from John nor Egret. Alright, let's take a look at key transparency model with a bit more detail. So at the heart of the key transparency model, we got the service provider, which keeps the public key directory and periodically posts commitments to the directory on the bulletin board, along with some auxiliary data, which we call it the invariance proof. I will in the future slide elaborate more on what the invariance proof is. And what are the functionalities that we actually expect from a key transparency scheme? So the first functionality is the lookup functionality. For example, John might query Egret's latest public key. But the other functionality, which is less intuitive and in fact harder to achieve, is called proof of consistency, which basically proves a public key has not changed from some epoch I to epoch J. For example, John might ask for a proof that his public key has not changed since last year. But you may ask, why does John want to know his public key has not changed since last year? Well, consider John goes offline in epoch I and comes back online in epoch J. So if he only looks up his public key at epoch I and epoch J and check their equality, it does not suffice, because the server might do a ghost key attack. So what is a ghost key attack? The service provider basically changes his public key whilst he's offline to something malicious and reverses it back to original before he comes back online. So if John doesn't check those intermediate epochs, he's not ever gonna find out that he was being impersonated by the Night King. And the way that the proof of consistency here helps is that he can ask for a proof of consistency for the period that he was offline to make sure he was not impersonated by a malicious public key. And as it turns out, different approaches to proof of consistency is what makes different schemes quite different. So at a high level, we have three approaches to proof of consistency right now. These include naively performing lookup for every epoch, used in earlier works like conics, the version invariant used in works such as Seamless, Parakeet, and Optics, and we have the random version invariant, which we introduced in Aegon and Irondeck. Alright, let's see a bit more detail on each of these approaches. So the simplest way to proof of consistency is naively performing a separate lookup for every intermediate epoch, retrieving all these public keys and checking that they're all equal. But this requires J-I computation and communication both for the client and server, which is not ideal, and basically the version invariant try to improve on this. So the way that the version invariant works is that every public key is assigned a version, and every time a public key changes, the version is incremented by 1. And the cool observation here would be that the way it actually simplifies proof of consistency is that a proof of consistency from epoch I to epoch j would be just equivalent to checking that the versions are equal at epoch I and epoch j, which is really cool because we just reduced j minus I proofs to only j minus I lookups to only performing 2 lookups. But one fundamental question here that I sort of like let it slide is that how do we actually order the version invariant? How do we actually make sure that the server is incrementing these versions honestly? And this is where the proof of invariance comes into play. So the server, with every epoch, also publishes a proof of invariance, which basically proves that the versions are incremented correctly. Concretely, for optics, parakeet, and seamless, this proof of invariance is just simply the list of updates. And what happens is that given the previous commitment and the list of updates, some parties who are called the auditors, they recompute the new commitment and ensure that a new commitment is computed correctly by the server. And just giving you heads up for what's coming next is that this list of updates is large and basically makes the auditor's computation expensive. And it cannot be done by people with like mobile phones and weak devices. But we'll see it in a few slides. All right. So far, we have an understanding of what key transparency is, what functionalities it has, and a high-level overview of the existing approaches. Next, I want to talk about the drawbacks of existing app schemes which are already used in deployment. So there are 3 main challenges with existing deployed systems, including seamless parakeet and optics. These drawbacks are self-auditability, perfect privacy, and history pruning. I'm going to go through each of these with a bit more detail. So, as it turns out, the auditor's proof, which is the invariance proof, is large and expensive to verify. And as I said, it's linear in the number of updates happening in that epoch. Concretely speaking, for WhatsApp key transparency right now, it's equivalent to downloading and hashing 80 megabytes per minute, which is quite expensive for a mobile phone user to be constantly online and downloading 80 megabytes and hashing it. And hence, the auditing task of WhatsApp key transparency is delegated to Cloudflare. It means billions of users are trusting a single identity to do the auditing on their behalf. And by the way, I just want to quickly say in parentheses, there's been attempts to making the auditor proof sync via proof systems, including ZK Snarks, for example, Verdict and Hackathon, but generally speaking, these solutions do not scale due to the high cost of the prover. But that's a very long discussion itself. I don't want to get into details of that today. The second challenge is perfect privacy. So just giving you context, privacy is crucial in the context of key transparency. For example, lookups should not reveal the pattern of changing keys. Otherwise, an adversary observing that a user changes their key doesn't change the key regularly, it makes a potential target for them. And as it turns out, tree-based solutions do not provide perfect privacy. For example, Seamless, which is the backbone of WhatsApp key transparency, during every lookup reveals the last time that a key was updated. And the third challenge is history pruning. So the tree-based models are based on an append-only tree. And due to the append-only nature, all the unnecessary historical data are kept in the tree, and the size of the data structure grows indefinitely. And giving you concrete numbers, WhatsApp right now has a user base of 3 to 4 billion people, but the size of the underlying tree is more than 100 billion, because all the unnecessary historical data is kept in the tree. And that is like the other drawback of the existing deployed schemes. So observing these drawbacks, we propose a new paradigm in design of key transparency. So our first paper was Iron Date, and then we have like this follow-up paper, Agon, which improves upon Iron Date. All right, just giving you a summary of like the state of the art so far. We got like these tree-based approaches, like Parakeet, Optics, and Seamless. They scale really well, but they got a number of drawbacks that I mentioned in the previous slide. And there are also like a bunch of like other solutions which are based on algebraic accumulators, but I didn't really go through them because they do not scale. And hence, all the existing deployed schemes like WhatsApp, iMessage, Keybase, Messenger are all using the tree-based models. And then we introduce a new design, and a new paradigm in design of key transparency based on polynomials and polynomial commitment schemes called Irondict, and later we have Agon. So they scale perfectly similar to the tree-based solutions, and at the same time, they do not have the drawbacks I mentioned in the previous slide. And we believe they're quite fit for deployment. So Irondict was the first work. It achieves perfect privacy, it achieves self-auditability, and it scales well to a couple of billions of keys, dictionaries of size, basically 1 or 2 billion. But it's not horizontally scalable. For example, it is almost impossible for it to scale to 50 or 100 billion keys. And observing those drawbacks of Irondict, we propose Agon, which builds upon Irondict, and it is horizontally scalable, and the server-side computation is much more lightweight compared to Irondict. Just giving you a summary of the properties of Irondict, it achieves self-auditability. For example, for a dictionary of size 1 billion, the size of the invariance proof is 8 kilobytes, which is constant and independent of the number of updates happening in that epoch. It achieves fast forwarding, meaning that a client or an auditor can be offline for as many epochs as they are, and they come back online, they verify a constant proof, and basically verify the whole history of the key transparency, which is really cool because it doesn't require the auditors to be online all the time, unlike the previous schemes. And we believe that self-auditability without fast forwarding is essentially pointless because you cannot expect users with weak devices such as mobile phones to be online all the time. And finally, you choose perfect privacy. And what I mean by that at a high level is that our lookup proofs, our proof of consistency, and our commitments on the bulletin board do not reveal anything beyond what they're supposed to. However, Irondict had a number of drawbacks. It had a high epoch latency, it was not horizontally scalable, it had storage inefficiency, it did require a linear size setup. And observing those, we propose Agon, which is like, we can just call it like Irondict Plus Plus, or I don't know, Irondict Pro Max, something like that. And I just want to quickly say what is like the high level idea and the way that we build Irondict and Agon. So we call our technique the random version invariant. And just to quickly explain that, imagine your dictionary in every epoch is just a vector of public keys. And then we define these delta vectors, which is just a difference of two consecutive states of the dictionary, like just entry-wise difference. And as it turns out, the proof of consistency for sub index T is just equivalent to saying like the dictionary state at epoch I all the way to state J are all equal at index T. Or equivalently, we can just say like the corresponding delta vectors are all 0 at index T. And now if you want to formalize a ghost key attack here, it would be that like a ghost key attack is when like the dictionary at epoch I and J are equal, but not equal to one of the intermediate epochs. So a ghost key attack here will be basically saying like the sum of these delta vectors at index T is 0, given that the dictionary at epoch I and J are equal at index T. However, they're not all individually 0, means that there exists at least one of these delta vectors at index T which is not 0. And our high level idea in order to detect this is that we use randomness, so these differences cannot basically cancel out each other. And the way it works is that we define these rand vectors at every epoch, so the rand vector at epoch n is just equal to the initial state of the dictionary plus a random linear combination of these delta vectors. And basically key observation, which is what makes Irondict and Agon very efficient, is that a proof of consistency from some epoch I to epoch J is just equivalent to checking that the rand vectors at epoch I and epoch J are equal at index T. And as it turns out, the auditor task here would be ensuring that these rand vectors are computed correctly. And concretely speaking, it's just a constant number of hashes and group operations, which is quite efficient because the proof of invariance would be constant, independent of the number of updates happening in that epoch. Alright, seeing some numbers, so we have implemented Agon and compared it against WhatsApp key transparency, which is based on seamless prosperity. So for an equal epoch latency of 1 minute and a throughput of 1,000 updates per second, I mostly want to highlight the lookup latency for the server and the audit proof. As it turns out, the lookup latency for the server for Agon is much lower compared to WhatsApp key transparency, whilst it requires more computation, which is interesting. The reason the latency is lower because we require way fewer database reads compared to WhatsApp key transparency, but we require more computation because of how our privacy basically works. So yeah, for example, the latency for Aegon is almost like less than 50 milliseconds, while for WhatsApp is almost like 500, something like that. However, the audit proof size for Aegon is constant size, whilst for WhatsApp it grows linearly when the number of updates happening in that epoch. Concretely speaking, for Aegon it's like 250 bytes, while for WhatsApp is with this throughput it will be something like 80 megabytes and can be verified in around a second. And finally, I don't really have time. I just want to say like Aegon and Irondic are both generic. It's a generic design over any choice of polynomial commitment scheme. But for efficiency reasons, we go with this recent work that we had called KZH, polynomial commitment scheme. But they're generic. Basically, you can build new polynomial commitment schemes and initiate it with them. And finally, for details of Aegon and Irondic, please check out the paper of Irondic is already online. The paper of Aegon will be hopefully online in less than a month. And we've already given a talk on Irondic at Microsoft Research, and we'll hopefully give a talk for Aegon there very soon as well. And very special thanks to Malaysia Chase for hosting those talks. And thank you.